So I've got a number of things I want to do today. First, I want to just go over the project and summarize it and show you how to use Mathematica in kind of a fancy way to generalize it. It'll really show you the power of Mathematica. Next thing I want to do is I want to finally go back to that end of chapter 3 section and talk about something called the mean value theorem and its corollaries. Then we'll talk about something called L'Hopital's rule and then parametric curves. So that's a lot to try to get in. We're only going to be able to get the basics across on those subjects. So again, here's the wet lens problem. And what I'd like to do for you today is just say, what happens if I allow this cost and this cost to be unspecified parameters? Call them, say, A and B. Of course, in the problem, you can see A is $1.20 and B is $2 per foot. But what if I allow those to be something that can change? That might be a really useful thing because that could allow me to use calculus, use Mathematica in particular, to analyze what could happen. How does the answer for the minimum cost and the value of X corresponding to the minimum cost depend on A and B? That's the goal here. And so I did this morning with Mathematica. And let me show you what I did. I will share this file with you after class. So it starts out the same. D of X represents the distance across that triangle based on the law of cosines. I did actually end up rounding the number that was right there to the nearest whole number because it makes the numbers work out more nicely. That's, again, the distance across the wetlands. Coming back to this picture here, D of X is that distance right there. Based on this triangle, we use the law of cosines to derive that. And again, in this problem, we multiplied D of X by 4.7, and then we added 2.7 times X plus 450. But now that I've got unspecified parameters, D of X is going to get multiplied by 3/2 plus A plus B, 1.5 plus A plus B. Why? Because for the wetlands, you got the $1.5 per foot, then you got A and you also have B. You have A and you have B in dollars per foot, corresponding to the normal terrain installation cost plus the additional track hoe. And then with the other term, X plus 450 is going to get multiplied by 3/2 plus A because that's over normal terrain. So the 1.5 plus A needs to get multiplied by X plus 450. This is a function of X, but A and B are parameters. And if you want to use Mathematica's full capabilities for something like this, you need to use subscripts and put A and B in there as if they are variables. In other words, use underscores when you define the function. Great thing about this is, like I said, you can use it to solve this problem in a pretty powerful way. And also, you wouldn't want to do this by hand because it gets pretty messy. Here is the derivative. Not too bad, but watch what happens when I solve for where that derivative equals 0. Very, very complicated, okay? I would not want to find those answers by hand. By the way, I had no idea how complicated the answers would be. This is how complicated. But Mathematica can do it, okay? And we can trust Mathematica to do it and see what happens. It turns out, so these are two roots that would come from the quadratic formula. It actually turns out the one with the minus sign there is the one we want. The other root is one of those extraneous roots that doesn't really solve the problem. So what I did here now was I essentially copied and pasted this formula right here. That's the X coordinate of my critical point. I just copied and pasted it essentially right here. Like here's what I'm dividing by, for example. You can see that's the same as this. And I'm calling that X min. It's the X coordinate of what's going to be the critical point, which will be a minimum. And I can find Y min, the actual minimum cost, by plugging that into the cost function. The Y min formula is what you see here, and that's even more complicated. It's good that we have Mathematica. I definitely would not want to do that by hand unless I, was forced to. or if I could win $1 million or something like that, I would not want to do that one by hand. But Mathematica can do it in a split second. This code shows the graph of the cost as a function of x. So the horizontal axis here is x. The vertical axis is the cost. And you can see when A is 1.2 and B is 2, which is what they were in the problem description, we've got a minimum close to 400 for x and close to 3,000 for the cost. That black dot is at the minimum point. But now we can see what happens as A changes and B changes. Watch what happens as A increases. If I let A increase from 1.2 to something bigger, what happens to the location of that black dot? Watch it. Here we go. Ready? 1, 2, 3. It's moving upward and slightly to the left. As A increases, the x value that minimizes the cost gets smaller, and the actual minimum cost gets larger. The x value that minimizes the cost as A gets bigger gets smaller. So you want to, with a larger A, you want a smaller length right here, which would be a longer length across the wetlands to minimize the cost. And the cost is going to go higher, which should make intuitive sense. As that cost for A increases, the cost goes higher. What about if I increase B? B was the track hoe cost in dollars per foot. It starts out at 2. If I increase B, ready, 1, 2, 3, go. That point moves upward ever so slightly, but more clearly it's moving to the right. Interesting. As B increases, as this track hoe cost increases, then X increases. You want a longer value of X when B is higher. That should make intuitive sense because a higher value of X is going to result in a shorter value of D of X. And if B is higher, that means the track hoe cost is higher. You would want a shorter value of D of X there. We might wonder, how do the values of X min and Y min depend on A and B? You could even graph these as multivariable functions. This is a graph of the X location that minimizes the cost as a function of A and B. It's a multivariable calculus function. You can see here by looking at the graph, generally speaking, as A increases as you move to the right, this graph for any fixed D is going downward. As A increases, X, the X location of the minimum, goes down. On the other hand, if B increases, like this, move to the right over here, now you can see the X location of the minimum increases, just like I said. You could also graph Y min in terms of A and B. Looks like a plane. It's not a plane. It just looks like one. You can see a little bit of curvature right there. And generally speaking, yeah, it looks like, oh, I labeled this wrong. This should be Y min. This is the minimum cost over here. It looks like the minimum cost goes up whether A increases or B increases, which makes sense. If A and B both increase, that's definitely going to affect the total cost. It's going to make the cost go up when they increase. You can find partial derivatives of these functions with respect to A or B, and we can plug in numbers. This finds the partial derivative of the X location of the minimum with respect to A. Complicated, but hey, Mathematica can do it, and I can plug in my numbers. And with respect to B, and I can plug in my numbers. What is this telling me? These are derivatives. I can think of this in terms of linear approximation. The fact that this one is close to -20 means, for example, if A increases from about 1.2 to say 1.3, I should expect my minimum cost to go down by about $20. Times 0.1, which would be $2, because A increases by 0.1 from 1.2 to 1.3. On the other hand, if with the derivative with respect to B, if I let B increase a little bit, say from 2 to 2.1, this would say my minimum cost goes up by about 0.1 times 27. That'd be about $2.70. Okay, so there's a lot you can do here. I won't really explain this anymore. Just appreciate the fact, look how complicated that one is, that Mathematica is pretty powerful. Lots of things you could do on Mathematica that you definitely wouldn't want to do by hand. And I wouldn't want to do these on a calculator either, right? No calculator that I know of can handle this kind of thing. Right? Those are just way too complicated, but Mathematica can do it. Any questions at all? Just trying to get a big picture idea of the things you can do. And like I said, this would be really useful because what if those costs change? How is that going to affect the answer? Okay, that would be a useful thing to know, not just for pipelines, but there are other problems like this where you might be interested in knowing what happens as parameters change. All right, our next topic for the day is the mean value theorem. So I've had you read about this before, although maybe you've skipped the reading. At the end of chapter 3. The mean value theorem is certainly one of the most important theorems in calculus, though you wouldn't necessarily get that impression just by looking at it. Mean value theorem. In fact, I like to sometimes abbreviate this MVT and start shouting kind of like MVT, MVT, like most valuable theorem, but it's called the mean value theorem. What does it say? It's an abstract theorem. It applies in certain abstract situations, though when we apply it, we often apply it to particular situations. It says, suppose f is a real valued function, so its outputs are real numbers, which is continuous on an open interval here, a comma b, that represents the set of numbers between, oh, excuse me, I actually want a closed interval. Closed interval from a to b, that it represents the set of numbers between a and b, including the endpoints. Okay, so this is a number line. A and b are numbers, a is less than b. This notation with square brackets refers to all the numbers in this interval, including the endpoints. And differentiable on the open interval from a to b, that represents the interval from a to b that does not include the endpoints. It's same kind of notation as a point, but it does not represent a point in the usual sense. It represents an interval. You have to tell from the context. You might wonder why. We're assuming it's continuous on the closed interval and differentiable on the open interval. I will try to explain that. Then the conclusion is, then there exists a number c in the open interval from a to b such that f prime of c equals f of b minus f of a divided by b minus a. That's the conclusion of the mean value theorem. In any situation where you've got a function like this that satisfies these properties on these intervals, you are guaranteed, it's been proved, that there will be some number c between a and b. This means, since it's in the interval, this means c is between a and b. So that the derivative at c, the slope of a tangent line, slope of tangent to f at the point c comma f of c equals this quantity, which is really a rise over run. This is a slope of a secant line. Between 2 points on the graph of f, a comma f of a, and b comma f of b. Here, these notations here, these three things are points, whereas this thing is not a point. That's an interval, but these represent points. If you draw an appropriate picture, this seems completely obvious. If you draw a picture of a graph of a function, that's a nice function. It's continuous. It doesn't have any breaks in it, and it's differentiable, which means the graph is smooth, maybe like this. The truth of this theorem, if you think about it in the right way, seems completely obvious, because the tangent line, or the secant line between this point and this point is this line here. This point here is a comma f of a. This point here is b comma f of b. This is rise over run for that line. If you draw a right triangle in here, that distance right there is f of b minus f of a. And this distance right here is b minus a. That's a rise over run. That's a slope of that secant line. The theorem says there's some number c where the slope of the tangent is the same as the slope of that secant. So what you need to do is just visually see approximately where the tangent has the same slope. Maybe right about here, the tangent line has the same slope. These lines are supposed to be parallel. So for this picture, c is approximately right there. There can be more than one value of c that works. If your graph looks maybe more like this, then there'd be more than one value of c that works. But there's at least one value of c. In this case, there's more than one. There's three tangent lines that are parallel to this one. One right about here, one right about here, and one right about here. So there can be more than one value of c, but again, the theorem guarantees at least one. There won't be zero values of c that work. Okay, so it makes sense. We could illustrate the theorem with an example, though you should realize the example is just meant for illustration. For example, I could take a simple example, say f of x equals x squared. Let's say a is 1 and b is 4. That implies f of b minus f of a divided by b minus a is 4 squared minus 1 squared over 4 minus 1 is 16 minus 1 is 15 over 3, which is 5. And the theorem says there's some number c between 1 and 4 where the derivative of this equals 5. Well, that's pretty easy to solve for because we can find the derivative. We get 2x. We can set that equal to 5 and solve for x. We get x is 5 halves. In other words, that's the c in the theorem. F prime of 5 halves is 2 times 5 halves is 5. It matches that. 5 halves is 2.5. This number does happen to be halfway between a and b. It's the average of a and b. When you've got a quadratic, that'll be the case. But the c will not always be halfway between. You can see in this picture, it's not halfway between a and b. Okay, so that's what the mean value theorem says and how to understand it with a picture and with an example. Examples and pictures are not proofs. The proof of this is actually very difficult, much more difficult than you might imagine, and requires really truly understanding what real numbers are, which sounds strange because, like, don't we already know what real numbers are? And the answer is, you know less about real numbers than you think you do, okay? Or maybe you don't, I don't know. So the proof of this from more basic principles is actually pretty hard, and we're not going to prove it. You'll be happy to know. But what's it good for? What would we use it for? I'm not going to take the time to do this proof in class, but one thing it can be used for is to prove something called the increasing function theorem. the increasing function theorem says, suppose, excuse me, once again, f is a real valued function which is continuous, once again, on a closed interval from A to B, and differentiable, has a derivative on the open interval from A to B. So same setup as the mean value theorem. If f prime of x is greater than 0 for all x in the open interval from A to B, the conclusion is then f is strictly increasing on not just the open interval, but actually the closed interval, on the closed interval from A to B. Now, I'm not going to take the time to prove this. It can be proved fairly easily, actually, with the mean value theorem. So that's one application of the mean value theorem. But let's just think about what this means. You got a nice function, continuous on a closed interval, differentiable on an open interval. The graph doesn't have any breaks in it, and the graph is smooth. No corners in the graph. Remember, where you have corners, you can have lack of differentiability. Remember that from chapter 2. This says if the derivative is always positive, if the slope of the tangent is always positive for every x in the open interval, then f has to be going up. Its graph has to be going up, increasing on the entire interval. That should make good intuitive sense. If the slope of the tangent line is always positive, how could the graph of f be doing anything but going up? How could it possibly be going down at some points in the interval or something like that? It's not possible. Okay, so the increasing function theorem is an example, and we really have used this when we've talked about, for example, the first derivative test. There's also a decreasing function theorem that says if f prime is negative on the interval, then f is strictly decreasing. And that can be used to prove the first derivative test for a local maximum. Maybe your graph looks like this, and you've got a critical point right there. What we've done with the first derivative test is we've made number lines, and we tested the sign of f prime, positive here, negative here, and we said there must be a maximum here at C. That's because the function's got to be increasing when x is less than c and decreasing when x is greater than c. So the increasing function theorem and the corresponding decreasing function theorem can be used to prove the first derivative test, which we've used to test local extreme points. So they have applications to optimization. Couple real subtle points here, but important. This theorem does not say, if f is strictly increasing on the interval, then f prime must be positive. In fact, there's a simple example of a function that's strictly increasing, but its derivative is not always positive. That simple example is f of x equals x cubed on any interval that contains 0. This graph looks about like this. That function has a graph that is always strictly increasing on any interval, including any interval containing 0. However, f prime of 0 is 3 times 0 squared is 0, and 0 is not bigger than 0. So, seems like a subtle point, but it is important. Just because a function is strictly increasing doesn't mean the derivative is always positive. It could equal 0 at certain isolated points. Okay, so something to be aware of, including for exam 3, and take note of and make sure you think about, not just right now, but at various points before exam 3 here. Can I clarify anything?
Exam 3 is next week, right?
No, I think it's the week after. I think it's the last week of class.
Do we have the final and exam 3 in the same week?
Not in the same week, no.
Okay.
All right. I did want to also talk about why we have open interval here and closed interval there, but I think I'll save that for Friday. Next topic is something called L'Hopital's rule. Here's how you spell it. Actually, sometimes people spell it with an S in here. I usually avoid the S. It's a French name. Actually, L'Hopital was an aristocrat. He really wasn't a mathematician. He got a mathematician to write a calculus book for him, and because he funded it, he got his name on it. And so then L'Hopital's rule stuck. L'Hopital's rule is a method for computing certain limits. And as far as today goes, we'll just do a few basic examples. You'll find more examples that are harder in the reading. But because we're low on time today, we'll just do some basic examples. Let's say we wanted to compute the limit as x goes to 0. Let's say sine of x over 4x. If this limit exists. So you look over this, it should be very unclear what to do. You can't plug in 0 because you'd be dividing by 0. Can you cancel the x's? Not precisely, though what we'll end up doing is in some ways equivalent to that. Does the limit even exist? I mean, we could try plugging in numbers for x that are close to 0 but not equal to 0. Let me make sure I'm in the right mode. Oh, forgot I got to go back to radian mode now. What if I plug in 0.1 for x? So I compute sine of 0.1 divided by 4 times 0.1. I get this. Okay, let's try a number that's even closer to 0. Sine of 0.01 divided by 4 times 0.01. You look at those numbers, it seems like perhaps this is getting close to 0.25. Let's try sine of let's go 4 zeros and a 1. 1, 2, 3, 4, 1. Divided by 4 times 0.12341. It's rounding it to 0.25, okay? It actually doesn't equal 0.25 exactly. It's rounding it. It's so close to 0.25 that it says, let me just go ahead and round it to 0.25. Does that mean this limit is 0.25? 1/4. It does. It actually does. That's an accurate thing. It's not calculator mistakes or anything. But how would you verify it more rigorously that the answer is 1/4? You can use something called L'Hopital's rule. This fraction can be described as what's called a 0 over 0 indeterminate form. That doesn't mean you can divide by 0. Even though I'm writing 0 over 0, that does not mean I'm dividing by 0. I'm just describing this fraction as being something where both the top and the bottom go to 0 as x goes to 0. Really, I probably should include the limit sign in this description of an indeterminate form. In such a situation, when you have a 0 over 0 indeterminate form, it's not the only situation, but this is one example. You can use L'Hopital's rule to try to evaluate this limit. You might succeed, you might not. L'Hopital's rule is true, but it's not always helpful. It does turn out to be helpful in this case. How do you do it? What you do is you differentiate the top and you differentiate the bottom and form a new fraction. The derivative of the top is cosine of x. The derivative of the bottom is 4. I differentiated the top and the bottom individually. I did not emphasis on the word not use the quotient rule there. I'm not differentiating this fraction. I'm differentiating the top and the bottom individually. What I'm doing in the abstract could be written like this. Let me make this 0 and a actually. In the abstract, what I've just done is I've done this. Okay, but you can only do this when it's an indeterminate form, like a 0 over 0. If it's not an indeterminate form, L'Hopital's rule gives wrong answers if it's not an indeterminate form. So, second main lesson about L'Hopital's rule is do not use it if it's not an indeterminate form. That's what it would mean for this to be an indeterminate form. F of a and g of a would both be 0. So is it clear what I did? This is my f of x. F of x is sine of x. The derivative of that is cosine of x. This is my g of x. G of x is 4x. Its derivative is 4. But now, this is a limit that's easy to compute because you're not dividing by 0. You can plug in, this is continuous everywhere. You can plug in 0, get cosine of 0 over 4, which is 1/4 or 0.25. There we go. There's the answer. Sometimes you have to apply L'Hopital's rule more than once in a given problem. Let's consider this example. The limit as x goes to 0 of 1 minus cos x over 5x squared. See. Is this a 0 over 0 indeterminate form? That's the first thing to check. It is. You plug in 0 on the top. Cosine of 0 is 1. 1 minus 1 is 0. Plug in 0 on the bottom. 5 times 0 squared is 0. This is a 0 over 0 indeterminate form. Therefore, we are allowed to use L'Hopital's rule. So I differentiate the top and the bottom individually. It's not the quotient rule. The derivative of 1 minus cos x is sine x, right? Because the derivative of cosine is negative sine. And the derivative of the bottom is 10x. Hey, that's another 0 over 0 indeterminate form. Use L'Hopital's rule again. Now you've got something that's not a 0 over 0. This is continuous everywhere. The answer is cosine of 0 over 10, 1/10. Try plugging in a small number for x and see if that seems right. 1 minus cosine, say 0.001 divided by 5 times 0.001 squared should be close to 0.1. Yes, very close to 0.1. All right. L'Hopital's rule can be applied with other kinds of indeterminate forms. There are ones called infinity over infinity indeterminate forms. say something like that. Now the top and the bottom are not going to 0 as x goes to infinity. They're going to infinity. This is an infinity over infinity indeterminate form. I can't literally plug in infinity because I'd get infinity over infinity, and that doesn't equal anything. This is another situation where L'Hopital's rule can be applied. Differentiate the top and differentiate the bottom. And lo and behold, you get a constant function whose limit is itself. But hey, we already knew that because this is a rational function where the degree of the top and the bottom are the same, first degrees. So you look at the coefficients of the highest powers and take their ratio. We already knew the answer was 5/4, but this is verifying it with L'Hopital's rule. By the way, to emphasize, L'Hopital's rule should not be used if it's not an indeterminate form. If you tried applying L'Hopital's rule here, you'd get the wrong answer because the derivative of 10 is 0. You'd be dividing by 0. Don't apply L'Hopital's rule here. Don't apply it here either. And don't apply it here. Okay? Only when it's 0 over 0 or infinity over infinity can you apply L'Hopital's rule, though there are some other situations you'll read about where things can be modified in a kind of tricky way to allow you to apply L'Hopital's rule. Any clarifications that I can make? With this form of it, the reason it's true is based on essentially linear approximations, and the book does describe that. With this form of it, it's a bit harder to explain, harder to prove. Okay, but still true. You can still use it. All right, take a breath. Just one more topic. We've done 3 topics so far. One more topic, and that is parametric curves. If I let x equal cos t and y equal sine t, as t varies between 0 and 2 pi, if you plot the corresponding values of x and y, what will you get? If you pick some different values of t, like t is 0, say pi over 6, pi over 4, pi over 3, pi over 2, pi over 6 is in the ballpark of 0.5 something, pi over 4 is 0.7 something, I think. Pi over 3 is a bit bigger than 1, pi over 2 is about 1.57. And I could keep going here, but I won't. Plug those into these formulas in place of t. Cosine of 0 is 1. Cosine of pi over 6 is square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. That's about 0.86. This is about 0.707, I think. Cosine of pi over 3 turns out to be a half, and cosine of pi over 2 is 0. Plug those same values of t into the y equation. Take their sign. Sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 3 is square root of 3 over 2. And sine of pi over 2 is 1. If you plot these points in the xy plane, what will you get? You'll get a picture about like this. That's x equals 1 there, and this is y equals 1 right there. And in fact, if you think more carefully about this, in terms of the unit circle definitions of cosine and sine, for any value of t, we'll be at a point on the unit circle, centered at the origin with a radius of 1. For any value of t. Because cos squared t plus sine squared t equals 1. So for all t, these points are on the unit circle. which has equation x squared plus y squared equals 1. But it's more than just that they're on the unit circle. The unit circle gets traced out at a constant speed, in fact, as t increases at a constant rate. I keep moving around the circle at a constant speed and end back where I started when t is 2 pi. When t is 2 pi, I'm back at 1, 0. This is representing uniform circular motion. On your calculator, you'd want to be in parametric mode to graph this. Go to the mode, go to par instead of function mode. If you then go to your y equals screen, it'll look different. You can type cosine t, sine t. When you go to the window screen, it'll look different as well. Pick a t min and a t max. This is 0 to 2 pi actually. That number there is, I'm not sure, maybe pi over 36 or something. I don't know what the t step is. I'll just leave it alone. X min and X max, let's try negative 1.5 to 1.5. Y min and Y max, negative 1.5 to 1.5. Okay, now I'm going to hit graph. And when I hit graph, you're going to see the unit circle be traced out, and watch the motion of it, though. It's at a constant speed. Ready? 1, 2, 3, go. Doesn't look like a circle. That's because the window is not set to make it look like a circle. If I pick a different window, let's see here. I'm forgetting how to do this window. There's like a zoom square, I think. There we go, z square. We'll pick it so that the it'll look more like a circle. There we go. Let's trace out at a constant speed. It's representing more than the circle. It's representing motion, uniform circular motion. That's what parametric curves are all about, is representing motion. Not necessarily uniform circular motion, but motion in general. What about if I modified this a little bit and replace the t with, say, 3t? Oops. And replace the, for the cosine, and replace the t and the sine with, say, 5t. Still going to keep the same window. Is this going to be on a circle? No, it won't, because the inputs of the cosine and sine are different. Although, whatever points we get, they'll always, the x and y coordinates will always be between negative 1 and 1. Here we go. You ready? 1, 2, 3, graph. What fun. There's the picture. Let me try slowing it down a bit. Let me do a smaller t step. That should slow it down. 0.01 or something. Here we go. Very pretty picture. Definitely not a circle, though. It's called the Lissajous figure. And what you can maybe do is you could imagine you're driving around a parking lot like this. You're looking down, straight down in the parking lot, and you're driving your car around like that, and hopefully not getting stopped by the police. Okay? It's a motion, though. Being a motion means there's going to be a speed. What is the speed? Given x equals f of t and y equals g of t, what is the speed as a function of time because you're not necessarily going at a constant speed. And in fact, in this figure here, it actually was not a constant speed. Let's look at it again. Watch how it speeds up in the straightaways and slows down in the tight turns. Ready? Oops. I guess I actually have to change t-step. Slows down in the tight turns, speeds up in the straightaways, slows down in the tight turns, speeds up in the straightaways. The speed is not constant. And in fact, if you were driving around a parking lot like this, you'd have to slow down in the tight turns, just like you see here, of course, and you could speed up in the straightaways. What is the speed as a function of time? If we're thinking about this example, it was uniform motion, it was a constant speed. So that could be found as just distance divided by time. And in fact, since this is the unit circle, the distance is 2 pi times the radius, but the radius is 1. The distance around the unit circle is 2 pi, and the time it takes to go around the unit circle is also 2 pi. So the speed here is really 2 pi divided by 2 pi, which is 1. That's the constant speed. 1 unit of distance per unit time in this example. But in general, you can't do that. Here's the formula you need. Speed of t is square root of f prime of t squared plus g prime of t squared, which with Leibniz notation, you could also write like this. And that's your speed. As long as f and g are differentiable, you're assuming these derivatives f prime and g prime exist. Let's see if we can get Mathematica now to animate the Lissajous figure. That, again, this thing is called the Lissajous figure. By the way, you can get in the physics department, you can get them to make laser beams that look like this because they're using like mirrors that are oscillating really fast, and you can get the lasers to show up on the wall like that. It's pretty cool. Let's go ahead and see what happens with this example in Mathematica. So f of t was cos 3t, g of t is sine 5t. Unfortunately, if you just do parametric plot on Mathematica here, where you plug these functions into a list like this, it just gives you a static picture, which is still pretty, but that's not what we really want. We really want to see the motion. So we need to put this in a manipulate and let the right endpoint change. Unfortunately, it doesn't pick a constant plot range, but that can be fixed. I can add in a plot range here. Like that. There we go. So there's the same Lissajous figure. What's the speed? I could define it as a function of t, and I could use the square root button over here. F prime of t squared plus g prime of t squared. And I could look at its formula, but it's going to be more enlightening to graph it. plot the speed as a function of time. There we go. Isn't that pretty as well? So every time we're at a low point, like here, 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 and here, that means we're in the motion is in a tight curve. Every time we're at a high point where the speed is high, we're in a straightaway. So it looks like we're near a tight curve near t equals 1, t equals 2.2, t equals 4 point something. I mean, you could try to check and see if that seems about right. T is just barely bigger than, or real close to 1. We should be in a tight curve, like right about now. It's real close to 1. B is just representing the right endpoint of the interval here. Another tight curve would be when t is about 2.2. So when b is about 2.2, like right about there. Another one when b is about 4.1. Right about here. And finally, another tight one is when t is about 5.35 or something. Right about somewhere in there. Yep. Okay, so you can match up the graph of the speed function with what you observe in the animation to see where the speed is slower or faster. Of course, this is kind of herky-jerky here. You can slow it down to make it a little easier to see by pressing this button, this slower button here. That's a little easier to see. Okay. Those are the main things I wanted to emphasize about parametric curves today. We will re-emphasize these things on Friday. Let me emphasize one more thing, even though I'm not going to assign any problems related to this. We're about on Friday to start chapter 5, our last main chapter, though we'll talk a little bit about chapter 6 as well. Chapter 5 is all about integrals. Now, we talked about indefinite integrals already as the integral symbol applied to a function, and it just is saying find an antiderivative of that function. So for example, when I write integral of x squared dx, that's 1/3 x cubed plus c. That's the most general antiderivative of x squared. However, the perspective in chapter 5 is different. This is an indefinite integral. The word indefinite being used because it really represents infinitely many different functions. But in chapter 5, we're going to learn about definite integrals, where I have something called a limit of limits of integration, like maybe a 1 and a 5. And this no longer represents an antiderivative when you've got fixed numbers there. Instead, at least when the graph is above the axis, it represents the area under the graph. It represents this area. This equals area under the graph. Right there, whatever that area happens to be. Turns out that areas under graphs are really, really important in applications. You wouldn't understand why until we get into it, but they're really important. And one application of it is to find the area. If you find the area under this graph here, that will give you the distance traveled along the curve. Say that again. If you find the area under this graph here, that will give you the distance traveled along the curve. And in fact, I can even do it real quick here. In Mathematica, I can use something called n integrate speed function. T goes from 0 to 2 pi. Mathematica is claiming the area under this graph is 24.6 units. And I have no reason to doubt that that's wrong. That's right. It is right. What that means is the distance traveled along this Lissajous curve is 24.6 units. Now, the units of area would be square units of distance, and the units of distance would be regular distance units. So the units are off, but the numerical values are the same. The area under this graph numerically is about 24.6, and that is the distance traveled along this curve, about 24.6, as t goes from 0 to 2 pi. That's a lot of information to take in, as always, maybe more than usual. Put in good effort on really trying to understand these concepts. They're really key to the class and applications of calculus. All right, that's it for today. See you on Friday.